So today I'm going to talk to you about sharded consensus, basically an approach to scalability known as sharding, but applied to consensus protocols.
This presentation will be kind of somewhat closer to practice, so it'll be about taking some of the existing research into consensus algorithms, sharding, and other things that we've done over the last few years, and seeing how they kind of concretely translate into what's actually going to be deployed in Ethereum land in the kind of short to medium term future.
We kind of need to imagine, if we're going to have scalability, that nodes will only do work that pertains to certain decisions. Like if they're only interested in some decisions, then somehow they should only have to do some of the work. Otherwise, we're not going to get any scalability. Kind of more example, a little less theoretical, a little more concrete part of the talk, where I'm going to talk about like how we do this, actually come up with these sharded consensus protocols.
Like I think if we look at what's been happening currently, like most of the spec that we released yesterday has basically been written by 4 people: myself, Danny, Justin, and Xiao Wei.
So today I'm going to talk to you about sharded consensus, basically an approach to scalability known as sharding, but applied to consensus protocols. So here's the little outline of my talk. I'm going to try to get through it in about 20 minutes. So we're going to give you a little primer on consensus protocols and sharding, basically just the minimum that's required to give the rest of my talk. Then I'm going to talk about sharded consensus protocols kind of in theory, abstractly, and then I'm going to give a couple of more concrete examples of sharded consensus protocols that we've kind of worked on in CBC Casper research. And then I'm going to talk a little bit about things I didn't talk about, and then I'm going to conclude. So let's get started. What are consensus protocols? Well, they're kind of all about making decisions in a distributed system in a way that's consistent. And this in the context of all the things that can happen in distributed systems, like faults of various kinds. Normally we talk about safety and liveness, the idea that these nodes that are kind of somehow running these distributed systems don't make inconsistent decisions, and they eventually do make decisions. And there's some other things we want that I'm just not going to cover here for the sake of time. So consensus protocols decide usually either on, well, they decide on values, we're going to call it consensus values, or on predicates of values. So rather than deciding on the whole value, say, okay, the value has this property. And in a binary consensus protocol, we're going to decide on a bit, 0 or 1. In the blockchain consensus protocol, instead, you decide that like some block is in the chain. You don't ever decide on a blockchain because it can always grow, but you decide this block is in the chain. And usually decisions are taken to be somehow output by the consensus protocol or committed to by the nodes in the protocol. So, a decision on a value is consistent with a decision on a value if they're on the same value. In this case, give an example of like 3-string 110 being consistent with a decision on the 3-string 110. Predicates are consistent if there's a value that satisfies all of them. So a decision that says the 3-string starts with 1 and a decision that says the 3-string starts with 0 are consistent because there's a string, for example, 110, that satisfies both. So the question I'm answering here is like, what does it mean for decisions to be consistent? And this means something slightly different in the context of deciding on values than deciding on predicates of values. And you're going to see that this is important in sharding because we're not going to be able to decide on the whole value because it's too big. We're just going to decide on predicates of values, which will let us say things about parts of the value. So some of this was really to say that consensus protocols are about making decisions about a predefined domain of consensus values. So different consensus protocols have a different notion of what it's deciding on, and consensus protocols are about making decisions on this domain of consensus values, be it by deciding on values directly or by deciding on predicates of values. Great. So hopefully that's super clear and relatively completely uncontroversial. Now we're going to talk about sharding. And here we have a sharded glass. It's very, very appropriate. So sharding is all about splitting up the work of a distributed system in order to scale its capacity. So really, fundamentally, the idea is we're going to try to scale distributed systems, scale their capacity, whatever that means, by splitting them up, whatever that means. Sharding, kind of got this from Wikipedia, was either coined by the Computer Corporation of America or by through this video game Ultima Online. It's about they used it really to mean using more computers as part of the system in order to either replicate or distribute the load. But fundamentally, kind of, if something's sharded, what we really mean is like it has more than one part. Fundamentally, sharding means there's more than one. It's like a bit is not sharded. This is kind of a really true thing. I hope you'll believe me. That a bit can't be sharded. There's no way to shard a single bit. And that kind of means that a binary consensus protocol is not sharded. There's no way to have a binary consensus protocol, a protocol that decides on a bit that is sharded. And that's going to provide us a nice little window. It's talking about sharded consensus protocols. Because at least we know something that, we know a consensus protocol that can't be sharded. Because any consensus protocol that's defined on the domain of consensus values bit can't possibly be sharded. Because sharding really means that there's more than one thing that we're deciding on at the end of the day. So we can't have a sharded binary consensus protocol. So what we really need is a sharded consensus value. So having sharded consensus value is a prerequisite to having a sharded consensus protocol. You really need to have a notion that your consensus value has multiple parts. It's fundamental. So remember, decisions are either on consensus values or the predicates. But because we want to increase the throughput of the protocol, we're going to insist that we're deciding on predicates rather than on the whole value. Because if we decide on the whole value, then nodes would have to decide on something for every shard. And instead, what we're going to do is imagine that nodes are interested in predicates that describe the value on some shards. So we're kind of imagining that nodes are not interested in the whole consensus value, but only some of it, which is possible because we're imagining that the consensus value has more than one part. Hopefully that all seems very straightforward. And somehow we have to have a notion of consistency of decisions, and it's like the same one as before. We haven't changed it at all. Basically, these predicates are considered consistent if there's a value in the domain of consensus values that satisfies all of them. So if you decide that like this sharded piece of the glass is a teacup, and I decide that like, this other piece is from a wine glass, those like are inconsistent decisions because there's no liquid holder thing that satisfies both. So, in consensus protocols, we have the opportunity to make inconsistent decisions. And in a sharded protocol, we have the opportunity to make inconsistent decisions about different parts of the system, about different parts of the consensus value, about different shards. So we got to choose different shards, things that are consistent for it to be a safe consensus protocol. So consensus protocols that are sharded require sharded consensus values. And the clients are interested in predicates of those values that only describe certain shards, in some sense. So I'm going to give you piggyback off of your hopefully prior knowledge and tell you that sharding clients are light clients. You've maybe heard about light clients before. And they're a kind of consensus protocol node that somehow needs to do less work than like a full node. We kind of need to imagine, if we're going to have scalability, that nodes will only do work that pertains to certain decisions. Like if they're only interested in some decisions, then somehow they should only have to do some of the work. Otherwise, we're not going to get any scalability. We need to imagine that nodes working on one shard don't need to hear everything about every other shard. Otherwise, we're not going to have any scalability. So we're going to imagine that sharding clients are light clients. And it's going to turn out that this is like, a perfectly appropriate decision. There's two kinds of light clients. There's light clients that don't look at all of the consensus value, and there's light clients that don't look at all protocol messages. And this is kind of a super interesting thing, so let me go into it. So we kind of are used to this kind of light client, or what I call a consensus value light client, where instead of the consensus value being the whole blockchain, you have a header chain instead. So consensus value light clients, they're really about using the commitments of proof systems as consensus values so that clients don't need to know or don't need to ask about the full consensus value when they're asking about predicates of the consensus values. They look at like a Merkle root, for example, and they ask about properties of this Merkle root, which they can do through a crypto proof system. So consensus value light clients really are about, instead of putting the whole consensus value in the consensus protocol message, instead, you just use a Merkle proof or some kind of commitment to some kind of proof system that lets you prove things about the consensus value. So rather than the client having to have access to the whole consensus value, it can receive proofs, basically like witness data that shows them things about different parts of the full consensus value. So, the blockchain header chain is an example of this kind of light client that basically minimizes the consensus value from including all these transactions and all this stuff that's in the blockchain to just Merkle proofs, Merkle commitments that can be used by light clients who are only interested in some part of the consensus value. So by kind of partitioning up the consensus value and using proof systems, clients can have access to and the ability to look at less of the consensus value. The blockchain header chain is an example, but also any sharding solution where you have something of the sort that you have like headers for every shard in the same chain, like a single consensus protocol, but the different headers affect changes or correspond to blocks that affect changes on different shards. This is like a kind of consensus value like client only approach to sharding. There is, though, another kind of light client, which I call protocol message light clients. These clients only receive certain protocol messages. They have some kind of filter on messages, and they know to only receive the ones that are relevant to their decisions. Maybe they only receive messages from certain shards, for example. So if you think about like the world of blockchains today as a big sharded system, then like the fact that you only download Doge blocks when you're interested in Dogecoin corresponds to this kind of protocol message like clientness. Instead of downloading all the messages from all the chains, I only download the ones that I'm interested in. Also, sharding solutions where different validator sets are responsible for consensus on different shards tend to have this property where you can only download messages from certain validator sets because you're only interested in decisions on those shards. So there's two kinds of light clients, these consensus value light clients, which look at less of the consensus value using proof systems. And then there's this other kind of light client called the protocol message light client, which doesn't need to look at as many protocol messages. So there's two ways that we save, by not looking at all the consensus values and by not looking at all the messages. So now I'm going to move to this kind of more example, a little less theoretical, a little more concrete part of the talk, where I'm going to talk about like how we do this, actually come up with these sharded consensus protocols. Well, we start off by defining the consensus values. We have like a blockchain on every shard. And we have like, shard IDs to identify the shards, and then I define like sent and received message queues for every pair of shards or certain pairs of shards, that keep track of the messages that were sent and the messages that were received from different shards, among some other things. Here's like a little code snippet from our the CBC Casper GitHub and our ETH sharding POC. We have a bunch of different things that are in a block, including the shard ID, a previous block, the transaction log, the sent log, the received log, sources, which are like things from, like the blocks from other shards that we're receiving messages from, virtual machine states, all sorts of stuff that is like part of the data structure of a block. So we define first we define the domain of consensus values that the protocol is interested in, and that nodes are going to make decisions about. And then we define a fork choice rule, which governs kind of which validators have control over the state of the consensus on which shards, and which makes sure somehow that the communication between the shards is consistent, or so that like the decisions that nodes make on different shards are consistent with each other. So like if we allow the chains on every shard to be completely independent, then there wouldn't be that much of a notion of cross-shard consistency. But instead, if we insist that, like, for example, a message that is sent should be received, and we shouldn't have like a finalized sent message that is finalized not received, which is like a kind of atomicity constraint, then, or as soon as you have any kind of constraint about the state that different shards should be on, then the fork choice, this kind of estimator, this thing that relates protocol states to consensus values, is going to have to do some work. And I'll describe that a little more when I get into an example. But so let me just take a step back. So the first thing we do is we define the sharded consensus values, and then we define this fork choice rule, which kind of, from a set of protocol messages, will give you a fork for every shard in this very blockchain-esque kind of way. And this is something that if you've read and already know about the CBC Casper framework, like you'll understand, because the estimator is like one of the main parameters of the CBC Casper family. So I'm going to show you some examples and kind of walk through what's happening here. So we have, in this case, a sharded consensus protocol with 2 shards corresponding with 2 blockchains, one in the parent shard and one in the child shard. Each of these each of these horizontal lines are identify messages sent from the same validators, and these red dots are messages that are sent across shard. And the fork choice rule of the parent is kind of completely independent, whereas the fork choice rule in the child orphans blocks that don't synchronize with the parent appropriately to make sure that all the messages are received once in order in the fork choice. So the kind of work here was first defining the block structure, which includes the shard ID and these messages, and then define a fork choice rule, which will pick out chains of this consensus protocol, chains of blocks from the blockchains produced by these nodes, in order to maintain this cross-shard consistency property. Here's something a little more sophisticated. In this kind of sharded consensus protocol, we have a notion in the consensus value of which shard is in the parent position, and a way for that to change over time. So this basically corresponds to consensus values that are a little more complicated because they allow for the shards to be in different positions. But still, the work is the same. We define the consensus protocols, and then we define the fork choice rule. In this case, the fork choice rule understands that some blocks, these purple ones, are root blocks, and these teal ones, these beige ones, are child blocks, and they have like different properties than the fork choice. This sharding solution demonstrates, this animation of the sharding solution demonstrates message routing, which again is just done with the fork choice rule and the consensus values by defining, the sent messages and adding a destination to each message and using a routing table to say where the messages have to be forwarded. So at the end of the day, the cool thing about the CBC Casper approach is that we can define rather complicated consensus protocols and fork choice rules without having to think again and again about the foundations of the consensus protocol stuff, because it's all inherited from this framework for making decisions in consensus protocols that the CBC Casper stuff offers. So in this protocol, a node that's following shard 3 doesn't need to know about everything that happens on shards 2 to 6. Like 2, 5, and 6, because the fork choice rule on the shard 3 doesn't depend on the fork choice rule on those other shards. And so they won't need to receive all the messages from these other shards, and we'll get some scalability via not receiving all the messages, which is the second sense of light client, that you're not receiving all the messages, but you're only receiving the protocol messages that are relevant to the decisions that you're making. So in future work, we have to define one of these are 2 of the kind of main pieces of work that are left to get the CBC Casper sharding solution to a point where I feel super happy. We don't want to have like a consensus values and fork choice rule that will let us have consensus on a non-deadlocking execution of the Ethereum virtual machine. So one of the issues, if you allow the Ethereum virtual machine to do cross-shard calls with synchronous calls, is that you can get into deadlocks, where a contract is waiting for a return value, and another contract calls it, and then it waits, and then you can get this cycle where everyone is waiting on each other. So if we have a consensus value and fork choice rule that will be basically the blockchains that record execution of the virtual machine that is deadlock free, that would be super cool. I have real reason to believe that it's possible. And this will allow basically synchronous calls in the virtual machine across shard. And another thing that we really need is the load balancer, so that the load on the different shards will be balanced over time, so that you can't, for example, overload one shard and make it prohibitively expensive to participate or use that shard. Load balancing also reduces the overhead of the routing protocol, and so we get a lot of scalability from load balancing. So if you're interested in these relatively tough problems, do contact. So I have a bunch of discussions that have been completely omitted from this conversation. So you might ask me, what about liveness? Well, liveness isn't really in scope right now because it's something that we're going to work on for consensus protocols, and for sharded consensus protocols, it's actually a very similar kind of solution will apply. If you like, the liveness strategies for individual shards for a single blockchain will also work on these shard chains. Non-triviality, well, I would love to talk about it, but there's no time. Validity and data availability are problems that we often talk about in relation to sharding, but which I usually omit or delay for later because I regard them as not consensus protocol problems. Like, consensus protocols are about making decisions in distributed systems in the context of mutually exclusive possibilities, but validity and availability aren't consensus protocol problems. There are other kinds of distributed systems problems, and the kind of problems that I think we can definitely solve once we have scalable consensus protocols. Validator rotation, would have loved to talk about, didn't really have time. Proof of stake and crypto economics. Also, you would maybe expect some of this from me right now, but since these systems are designed to be incentivized, we can kind of leave those conversations for later. And also, this talk is really just a distributed systems talk. So let me kind of wrap up by going over the main takeaways. So some things I hope you'll remember. Binary consensus protocols are not sharded. They cannot be sharded. Sharding consensus requires sharded consensus values. Sharding clients in a sharded consensus protocol are light clients. Sharded consensus protocols exist and are possible. There's actually a huge family of sharded consensus protocols. And sharding is a natural way to scale consensus protocols, especially if you're talking about consensus protocols that replicate something like a virtual machine or something that naturally has different components. So I hope that this is convincing. I hope that you're convinced. And thank you for listening. Thanks for having me. Please reach out and contribute to this work.
Okay, thank you very much, Vlad. And we will, again, defer the questions for later, have a joint Q&A. And now, please welcome Vitalik, who needs no introduction. But yeah, thank you very much.
I mean, it seems to be on.
Yeah. Okay, so I have 20 minutes and a lot of stuff to talk about, so I'll just get right to it. So Vlad gave a presentation on some of his research into CBC Casper and how CBC Casper can be extended into sharding contexts. This presentation will be kind of somewhat closer to practice, so it'll be about taking some of the existing research into consensus algorithms, sharding, and other things that we've done over the last few years, and seeing how they kind of concretely translate into what's actually going to be deployed in Ethereum land in the kind of short to medium term future. So yesterday we released the January pre-release. This is the first kind of release version of the spec of phase 0 of Ethereum 2.0. So, yay! Now, you might ask, well, what exactly is this? What exactly does this mean, right? We published an 8,000 word paper. We've published 8,000 word papers before. What's the significance? So, proof of stake and sharding have been part of the Ethereum roadmap since 2014. This is, Slasher is this very first early and unfortunately broken proof of stake consensus algorithm that we proposed back when we were originally starting to look at alternatives to proof of work. Sharding, we had a bunch of different sharding proposals. Hypercubes is one of the more kind of interesting and weird and spooky ones. But since then, the ideas have seen a lot of progress, right? So So we've had Casper FFG get kind of released and published and formally proven about 1 to 2 years ago. We had a lot of progress on sharding. So the research that we've been making over the last few years is kind of finally coalescing to the point where it's in a spec and it's in a concrete document that describes what people need to build. They're building it. The developers are claiming they're months away from a testnet, and it's finally coming into production. So what is this kind of Ethereum 2.0 structure, right? So how does this look like? So we have the structure is one where you have this kind of beacon chain in the middle. So it's this hub and spoke system where you have some chain in the middle and you have 1,024 shard chains, and these 1,024 shard chains are the chains that actually hold the transaction data that users are going to send that represents their desire to send money, trade CryptoKitties, or do whatever they want to do. So the system is also kind of connected to the current ETH 1.0 chain. This is temporary, so it's intended to go away eventually, but it is necessary because people do need a way of moving their existing stuff from the 1.0 chain onto this new chain. So it's being rolled out in phases. So phase 0 is proof of stake. And it has all of the kind of basic scaffolding in place to make all of the later phases possible and really do a lot of the work for them. Phase 1 is what's coming after phase 0, which is sharding, but specifically focusing on sharding of data availability. So sharding of a chain where you can put data on the chain, but the chain is kind of agnostic as to what the data actually means. Phase 2, state and execution. So this basically means not just being a place to put data, but also trying to interpret the data, trying to handle Ether transactions, transactions of tokens, virtual machine execution, this storage, things like storage rent, and all of these more complicated topics. And phase 3 and beyond is basically, well, we have a lot of other ideas about how we can incrementally improve the scalability and safety of the system over time, and we can kind of slowly layer them on top as these ideas come into fruition. So right now we're here, but really we're here. So the beacon chain, right? So the beacon chain, so first of all, in order to get onto the beacon chain, it is a proof of stake system. So to get onto a proof of stake system, you need to have 32 Ether, and you move it over to the beacon chain by sending it to a one-way burn contract. And then you publish a Merkle proof receipt onto the beacon chain. When it gets included in the beacon chain, you get inducted as one of the proof of stake validators of the beacon chain. So this basically means that you're moving your Ether from being Ether on the proof of work chain to being a deposit on the proof of stake chain. Now notice that for this to actually work, the beacon chain has to be aware of basically some root hashes on the ETH 1.0 chain so we can actually verify Merkle proofs. So this is why we do need kind of some link between the two. So this is what the beacon chain looks like. Now, one important thing to point out about this whole architecture is that it's designed to have a kind of separation of concerns between the proof of stake side and the sharding side. So the beacon chain basically is the thing that runs the consensus. But if there wasn't sharding, the beacon chain could theoretically run as a kind of non-scalable blockchain on its own just fine too, right? So if we wanted to, we could take phase 0 and we could add some space for transactions, and we would basically just be finished as a proof of stake system. Now, we believe scalability is really important, and so we're going all the way to add sharding, but the kind of design and architecture and a lot of things are fairly separate between the two. Although, as we'll talk about later, there are some really nice synergies. So time is broken up into slots, and slots are basically periods of time that are about 6 seconds long. They are grouped into epochs, so 64 slots in an epoch, and during each epoch, every validator makes one signature. So you have every slot you have a block, and every block gets attested to, so basically signed first by the block proposer, so first by the node that creates the block, and then by this kind of large randomly selected committee of other nodes that basically kind of sign these messages saying, I approve of this block and I think this is the block that is the head of the chain. So this happens every 6 seconds. You get these, a block comes in, attestations come in, a block comes in, attestations come in, the attestations get included in the chain, and this is kind of how the chain moves forward. Right, so these attestations actually have 3 different functions. So one of them is they contribute to the beacon chain fork choice. So a block that is supported by more attestations is the block that people will consider as being part of the correct chain. So we're not using the longest chain rule here, we're using something more complicated, but actually conceptually not too complicated, called LMD Ghost, that we'll talk about right now. It also contributes to finality, so over top of this there is simultaneously a asynchronously safe consensus algorithm that's running, and in attestations will also, at least in phases 1 and beyond, validate and commit to data on particular shards. Right, so these messages are kind of serving triple duty of kind of short-term agreement, medium-term finalization, and agreeing that data on shards is valid. So LMD Ghost fork choice. So the latest message-driven greedy heaviest observed subtree fork choice rule is an adaptation of Ghost, which was proposed by Jonathan Sampolinsky and Aviv Zohar in 2013 to a proof-of-stake context. So the idea of Ghost is basically, it's a fork choice rule that says, if you want to figure out which block is the head of the chain, then you start at the beginning, and if there's only one child, you go to the child, but if there's a choice between 2 children, you go to the child that has more messages supporting it. So here, 1 message supporting it, here 4, and then you go up to the next fork, then there's 3 choices, this one has 2, and you go here, and you keep going until you find the head. So Ghost is interesting because it allows us to take in more information, right? It allows us to take in information not just from blocks that arrive in sequence, but also from blocks that arrive in parallel. So for example, if you look at these 3 messages over here, all 3 of these messages are all really also votes for this block over this block, right? And so that's something the longest chain rule, like as in proof of work, does not take into account, right? The longest chain rule basically says this has a score of 4 and this has a score of 1. But really, there aren't 4 votes over here, there are 6 votes. And this is something that for us is really necessary because we have a hell of a lot of votes happening every 6 seconds, and we want to take advantage of these votes to kind of give the chain this really robust level of stability. And basically make one confirmation be, the equivalent of 50 confirmations on the existing chain. So this is one. Now, LMD Ghost basically says instead of looking at every message, we look at the latest message that a given client has seen from every validator. Now, this is the fork choice. We can also look at finalization. So FFG finalization, basically, this is kind of an adaptation of some classical consensus algorithms that tries to sort of dual-purpose messages that are already being part of a chain-based proof-of-stake algorithm in order to achieve this kind of finality property. And so if the chain is kind of progressing normally, and if enough messages, like really more than 2/3 of the messages, are agreeing on the same blocks for a span of 2 epochs, then that basically ensures that this block at the beginning of the whole thing gets finalized. And you can prove that unless something like 1/3 of all of the validators are provably acting in some way that's malicious, this block is just never going to get reverted. Right, so this is asynchronously safe and it's crypto-economically safe, and that's not something that you can get either in proof of work or in any chain-based proof-of-stake system. Crosslinks. So crosslinks are how proof-of-stake kind of interfaces with sharding. So you have shards, and each shard is also its own chain. And every validator on the beacon chain is also serving as a validator on some shard chain. Now, what we also want to do is we want to kind of commit blocks on the shard chain into the beacon chain for two reasons. One of them is so that finality on the beacon chain can also cause all of the blocks on the shard chain to be finalized, right? If block A on a beacon chain commits to some block on a shard chain and block A gets finalized, then whatever thing on the shard chain it was committing to was also kind of indirectly finalized by proxy. And it also is the kind of base engine by which the different shards can talk to each other, right? So shards know what the beacon chain state is, the beacon chain knows what the shards are, and so anything that happens on one shard, you can use a Merkle path to prove that it happened to some other shard. So these crosslinks are basically messages that get signed by a committee, which is some randomly selected 128 to 4,096 validators. Now, you might notice that this is relying on a kind of honest majority assumption. So basically, this is saying that you have a bunch of validators, and we're going to assume that the majority of them are honest, and so the majority of them are only going to sign on any particular crosslink if they actually think that that data is legitimate. Now, it allows a kind of semi-adaptive adversary, but not an extremely adaptive adversary. So what this means is that for each you might notice for each crosslink, or for each shard, the committee that validates that shard is randomly sampled. And pseudo-randomly sampled using some hashes that are created using a special algorithm inside of the blockchain. And what this means is that if an attacker has, say, some smaller, less than 1/3 percentage of all of the validators in the chain, then there is a very small probability that the attacker actually will be selected to have the majority of the messages in any particular committee, and so every committee will be safe. Now, if we had an attacker that was somehow capable of corrupting a specific number of specific nodes after the specific nodes were chosen, then this is not secure against that. But we do have some other defenses against that. So, BLS signature aggregation. Now, you might ask, well, we have a lot of validators. We potentially have a really lot of validators. The total ETH supply is about 105 million. The amount of ETH you need to become a validator is 32. You can divide 105 million by 32 yourself. That's a heck of a lot of validators that are providing signatures every 6 minutes. How can anyone validate all of this? So BLS signature aggregation is this nice cryptographic magic that lets us do this. Basically, these validators are all signing these messages that are about 200 bytes. And every committee is signing on the exact same data, which is really nice. Right? If every committee is signing on the exact same data, it basically means that we can really kind of computationally and data efficiently aggregate these signatures. And all we need is the message that they're signing, a bit string that represents what subset of the committee is participating, and you can combine all of these signatures into this one signature that can get verified extremely quickly. So the size is for 4,096 signatures is about 608 bytes, and it takes up to about 7 milliseconds to verify. Proofs of custody. So the question that this responds to is, can we do better than an honest majority for crosslinks? So far, well, from what I've said, the crosslinks are basically saying, well, we have these validators, and these validators are signing onto these blocks of shard chains, and they're only supposed to sign off on these blocks if they think the blocks are honest, and so if all of the validators, or most of the validators, are nice guys, then only correct shard data will actually be included. Can we do better than relying on them being nice guys? And I would argue we actually need to. So there is this somewhat famous paper on the validator's dilemma that was published 2 years ago. But basically the argument is most nodes are lazy and they're not going to validate data if they don't have to. And so what prevents people from switching to the much simpler and dumber strategy of just saying yes on everything? So proofs of custody basically are this mechanism where only if you have the underlying data for some block, you can run a computation on that data, generate a kind of new piece of data, commit to the Merkle root of the new piece of data, and later you have to reveal the secret seed that you used to generate the data, and once you reveal that secret seed, anyone else can, first of all, rerun the computation, verify that you did it correctly, and if you did it incorrectly, they can catch you with a fraud fraud proof, or if you just did not even have the data in the first place and you just made some random commitment, then they can make a challenge that you would not be able to respond to, and in either case, they would cause you to lose a lot of money. So this is a kind of economic defense against a possible lazy majority that should hopefully discourage people from being lazy. So these are kind of some of the basic technologies that we're planning on introducing. There's also some future directions that we're looking at. So there's this work that Mustafa Al-Bassam and I did on data availability proofs via erasure coding. So this is a technology that makes light clients potentially much more powerful. And basically, the idea is that if instead of committing to a Merkle root of just regular data, you commit to a Merkle root of data that you erasure coded, that in such a way that, say, any half of the data is needed to recover the original data, then a light client can just randomly sample Merkle branches, and if just from their random sampling they verify that more than half of the data is available, then they know that that data is probably there. And they don't need to actually download the whole thing to verify that enough data is there to recover the thing. So another thing we're looking at is Starks. Starks are useful for a bunch of things. They're useful for compressing Merkle branches. So if a client wants to verify that some block is correct, or that some block, the transactions in some block were correctly executed, they need a lot of Merkle branches to verify that the accounts that the transaction is claiming were modified actually are what the transaction is claiming. And this data is actually something like potentially 10 times bigger than the data in the block. And so if we use a Stark, then we can compress that, and we can get maybe another factor of 5 data efficiency. Yay. Verifying correctness of proofs of custody, verifying correctness of data availability proofs, in the really long term, verifying correctness of execution, which would be super nice, so we don't need to bother with things like fraud proofs. Casper CBC, also something that we have not integrated into the Ethereum roadmap yet, but it is something we're very actively looking at. And Casper CBC is nice because it allows us to significantly reduce protocol complexity. It allows the protocol to kind of better survive large portions of validators going offline. And there have recently been improvements that actually make Casper CBC efficient enough that if we wanted to, we can implement it. And like it would not cause the node requirements to shoot through the roof if the nodes actually tried to run the thing, which is something that we did not have kind of as strong an idea of before, but we do now. Yay. So these are some of the, just a quick overview of the ideas that are going into the Ethereum sharded system. So it's this combination of a lot of different technologies and ideas that are both kind of separate discrete technologies, but also work together and have a lot of really nice synergies between them. In terms of what you can concretely expect from all of this, I expect the next milestone will be to actually see test nets from some of the client developers. So the Ethereum Foundation has, or the Ethereum community really has this kind of structure that we deliberately tried to foster, where although the Ethereum Foundation and the core research team are taking a lot of effort to kind of spearhead development of the spec and of the protocol, especially in the earlier stages, the development itself is happening by these multiple independent development teams, including Prismatic Labs, Lighthouse, Nimbus, ChainSafe, and plenty Pegasus and other wonderful people. And they are like, if at this point, if you want to kind of hear about things like timelines for launch, then you actually don't want to ask me. I know less about that than they do, and you want to ask them. And from what we've asked so far, they're expecting testnets in a couple of months, and so I'm looking forward to actually seeing this go live, as I hope you are. So thank you.
Okay, thank you very much. Yeah, maybe I'll ask like 1 or 2 questions, and then we can open it up to the audience. So if you have questions, please maybe line up in the in the middle over there. Yeah, one question that I had is, can you maybe describe a little bit you mentioned this at the end, the difference between Casper's CBC and currently how the sharded consensus works, or how it's planned in the beginning?
Sure. So, I mean, first of all, like, there's multiple different families of Casper, and like, they have the same, like, Casper CBC and Casper FFG have the same name, but like, really, Casper basically just stands for Consensus Algorithm Spearheaded and Proposed by Ethereum Research. Like, these are, like, Casper FFG is like in efforts to try to kind of start from something closer to classical consensus and simplify and remodel it to be more like, to be more compatible with a chain-based approach and sort of merge the two, whereas Casper CBC is more of a from-scratch approach that tries to kind of more emergently derive finality from either a chain-based or potentially any other kind of system. So we've gone with what we have now mainly because it is what was ready at the time that we started solidifying the spec, and we have to solidify the spec and ship something at some point. But we're totally open, as I mentioned, we're totally open to and interested in integrating a kind of basic version of CBC and then looking at kind of other more advanced consensus technologies in the future as they kind of prove themselves to the point where it's clear that they're implementable and they make sense.
Yeah, I'd agree, and basically the way that I'd say is like the main differences is we have like methodological differences. I'm trying to follow this correct by construction approach and do things the very kind of disciplined approach, not worrying about optimization or the number of bytes that things are until the very, very end of the process. Whereas Vitalik is much more driven to implement and deploy something on like a more aggressive timeline, I'd say.
The Twitter trolls are telling us we have to ship. Raise your hands if you agree with the Twitter trolls. Yeah.
Everyone wants to ship. It's just a matter of like what, when, and how.
So, I guess talking about shipping, what do you view as the future of the Ethereum 1 chain once the Ethereum 2 chain starts? Will it slowly die out? Will we be stuck with it forever? What is the approach for sort of the switch from chain 1 to chain 2?
So I guess first of all, even before ETH2 launches and becomes usable, there is a lot of work kind of done by hardworking people like Alexei and like Lane and others on the 1.x front that are trying to do some short-term things like state size management to make Ethereum kind of more scalable and more usable in the short term, which is kind of the necessary. Then in the second stage, it's I expect like both chains will exist and people will kind of start migrating from one to the other when they feel comfortable, because there are a lot of benefits on being on a faster and a sharded system with much lower fees and a 6-second block time. At the very beginning, I expect kind of data publishing type applications, so like things like these decentralized Twitters, to probably dominate ETH2 because they don't require much infrastructure, and then over time more and more complex smart contracts move over. Eventually, I expect ETH1 to kind of probably be subsumed into ETH2 either as a contract on top of it or something similar. I don't know. V, what are your thoughts on this?
Well, I kind of hope that we do a hard fork upgrade of L1 of the ETH 1.0 into ETH 2.0, and that we don't keep a kind of side thing going on. But I think that the approach of not disrupting the chain while we're improving the system, makes sense. Like I think we should test things and get people using them before we consider anything like a hard fork upgrade.
In such a way that if someone were to use the Ethereum 2 chain, or the Ethereum 2 chain in effect wouldn't risk users that want to stay on the first chain. Okay.
Maybe not for now.
Not for now, okay. Then, yeah, I guess I'll open it up to the audience. So, yeah.
Hi. So during the transition from 1.0 to 2.0, are you going to use 1.0 blocks as the candidate blocks for the 2.0 to finalize on? Or so, like, how are you going to actually do the transition from the POW chain into the POS chain?
Ooh, okay. So the way that this works in the current spec is that the validators on the 2.0 chain are also running a mechanism where they basically vote on which blocks on the 1.0 chain to finalize. And then once the 2.0 chain has finalized some block on the 1.0 chain, then anyone who deposited up before then will be able to provide a Merkle proof receipt and join the 2.0 side. But this also has one positive side effect, which is that if a client developer wanted to, they could make a 1.0 client which kind of listens to and respects what the 2.0 finalization as something that actually finalizes that block on the 1.0 chain. So once that happens, they will be kind of tightly connected, so 2.0 breaking will break 1.0 as well. But if that happens, then the main benefit that you have is that on the 1.0 side, you no longer need to rely heavily on the miners for security, and so you can cut issuance by a lot.
So if that's the way you're going to transition, LMD Ghost does not necessarily say anything about having a tie, how quickly you can resolve a tie until the odd number of votes come in. So what are the guarantees, like network assumptions or the number of votes that you have to have? Like what are the environmental properties that you need to make sure that every app will at least be able to justify one block?
Sure. So the kind of formal properties of FFG are basically that you need, in order to have safety, you need at least 2/3 to be honest, and in order to have liveness, you need 1/3 to be honest, and you also need network synchrony. Now, in terms of network synchrony, I think if we were to try to make a formal proof, we probably would be able to prove something like that it works if the network latency was lower than a few seconds. But we've also done simulations, and one of the really wonderful things about Ghost is that Ghost can actually be pretty stable even if the network latency is several times larger than the block time. And according to our simulations, it actually works fine and keeps finalizing stuff even if network latency goes up to something like 30 seconds. So,
is that public? Is that simulation result public?
Yeah, I think it's GitHub, Ethereum research, and /collect disparity.
Thanks.
Hi. So in terms of being able to talk about a sharded consensus independently of data values, and then also just in general any kind of sharding for application layer concerns, given a resource that is necessarily shared across the entire ecosystem, or whatever we call all the chains running the network, which is namely Ethereum, right? Well, I would ask two things. One, is there any plans to make Ethereum not be in other words, be able to pay for gas in different currencies, like in stablecoins or something like that? But two, I could do, once I'm on the new chain, I could do an airdrop to every Ethereum user in a single transaction, presuming I have the gas to do that. And doesn't that cause a single checkpoint that requires every shard in the system to synchronize on one transaction? My question is, how much do concerns about that kind of synchrony requirements impact thoughts about performance, thoughts about how you structure the data, or do they impact them at all?
Well, the main thing that it factors into is actually discussion of gas limits and of how to make sure that you can't actually, do things that will slow down the whole system for really cheap. The point of gas is, one of the points of gas is denial of service protection. And these are really denial of service attacks that gas limits are meant to protect against. And so, it definitely is a performance concern, but it's also something that we have gas limits to deal with. And in terms of will gas be payable in other currencies, my personal preference is not in protocol. The protocol shouldn't support it. You can make smart contract solutions where someone else packages your transaction and they get reimbursed, but that in protocol gas should be paid in ETH.
To add to that answer in the context of the concrete spec that we're proposing, first of all, communication within a shard will be synchronous, but communication between shards will only be asynchronous. And so, like, you would do an airdrop, you could do an airdrop, but basically what you would really be doing is you would be creating a pile of Merkle receipts in each shard that the recipients or someone will at some point just have to pay the gas to kind of trigger on the other shards. So there won't be this kind of point of synchronization between different shards. As far as abstraction goes, I generally fully agree with Vlad that abstraction of gas fees is something that makes much more sense to do on layer 2 rather than layer 1. And I mean, for me, the reason why is that I think in order to mitigate proof-of-stake validator centralization, the job of being an optimal proof-of-stake validator cannot be too complex. And so if you require proof-of-stake validators to kind of have a lot of access to like financial markets and like requiring them to solve multidimensional optimization problems, that starts to become more difficult to achieve. But on the other hand, I think you can get a lot of the benefits just with like layer 2 protocols where people do whatever they want in kind of off-chain messages. Those off-chain messages pay fees to like intermediaries. Those intermediaries create transactions, and then they pay the ETH and they claim fees.
Thanks.
Hi. I think it's interesting, you know, when concrete kind of magic numbers appear in protocols and algorithms, and you've actually commented, like, for instance, in LMD Ghost, having, you know, one uncle making, you know, a given block have 2 pointers out makes the mathematical proving easier and so forth. 1024 for shards sort of, I think, appeared in FFG, and it's still there now. And on the one hand, it's a really big number, but I mean, Bill Gates one time said 640K, I think, was more memory than anybody would ever need. So I'm just curious, do you feel like you have a feeling of, you know, how optimal that choice is now as a first one, and then if it can be scaled over time and what sort of impacts it would have? This is a longer term question, but just curious.
Sure. I'd personally be totally in favor of the 1024 shard count being forked upward eventually. There's reason, I mean, so far, like, I have not found anything close, remotely approaching a kind of good, sensible governance algorithm for actually figuring out what the number should be in protocol. But other than, you know, like the usual validator voting or whatever. But it's, like, in terms of what the optimum is, I think, like, starting with something lower makes, I mean, it makes sense. I mean, 1024 is high already, but starting with something lower makes sense from a safety point of view. And as the system grows and gets proven over time, then sure, it should go up and more.
Okay, thank you.
Hi, this question touches a little bit on the load balancing Vlad has mentioned earlier for sharding. So I'm wondering, so far we are looking at shards which are static, so that they cover a fixed part of the state. So like shard 1, for instance, could contain state values A and B, and shard 2 could contain state values X and Y. So the question is it conceivable that I have dynamic sharding in the sense that each validator can pick what state values it's interested in? So just like that they're partially overlapping, but that there's no static shard?
I wouldn't let the validators pick, but this is the load balancer's responsibility in this kind of paradigm. The load balancer's responsibility is to move contracts around and to change the configuration of shards in order that the total gas consumption of the system is minimized, and so that the load is spread across the different shards. And definitely in this paradigm, you know, the shard contract assignment is not fixed.
Okay, thank you.
Hi, thanks for the great talk. I had a question about burning the transition from ETH1 to the new chain. So this burning of the coins seems to designed to prevent duplicate for coins or like airdrop coin. But what happens as the ETH1 starts to get deserted and gets less secure? A sort of a reorg attack comes and gives back people their old coins, and everybody would be happy, and probably they will still go back to the same hard fork situation, which could have been just at the very beginning just an airdrop.
So first of all, like I don't expect. So first of all, the economic value of the ETH1 token and ETH2 token we expect to be the same because it's all just ETH. So when you talk about the ETH1 chain being deserted, like being deserted by users doesn't mean that the proof of work reward goes down, right? And we don't expect the proof. Well, the only way the proof of work reward goes down is if we hard fork it down. And the only case in which it makes sense for us to hard fork it down is in the case where there is this kind of tight coupling where beacon chain finalization finalizes proof of work blocks, because then the ETH1 chain security doesn't depend entirely on proof of work. And if that happens, then 51% attacks on proof of work are not going to break safety in the way that you're talking about. But also, if we, like, this is, like, the current kind of 1 to 2 conversion approach is not set in stone. So if we want to, like, we could aim for something more aggressive. So, like, we could do something where, for example, even in one of the earlier phases, we add a big field into the beacon chain that contains ETH1 transaction, and we come up with some separate mechanism for calculating state roots. Okay. So, like, if that is what we want, or what we later decide makes sense, then there's like fairly simple ways to switch over to doing that.
Thank you.
Right, so given that the session is called the future of Ethereum, I would be thinking it would be appropriate to talk about maybe the future of the Ethereum Foundation. So is its role, firstly about its role primarily with respect to the project management of Ethereum 2.0? Is it going to assume some more of a leadership position, or is it going to be more into funding and giving grants to teams building onto it? Mm-hmm. Because my understanding is that let's say that the subject matter expertise on the matter of sharding, proof of stake, and so on, it's quite limited.
Sure.
All right.
So first of all, like I think if we look at what's been happening currently, like most of the spec that we released yesterday has basically been written by 4 people: myself, Danny, Justin, and Xiaowei. So I don't think that I definitely don't think that we're veering on the side of like not enough technical leadership for the 2.0 roadmap at all. And like I think it's like that's totally the right trade-off to make. So like even Bitcoin, you know, it was entirely centrally planned by Satoshi until it was released, and so things that are kind of in the earlier stages when there's a lot of technical questions to be figured out, like the core developers are doing that, and over time, like especially as real things get built and start being used on the blockchain, more and more stakeholders naturally come in, and I think that's something we've seen on the 1.0 side, and that's something we'll definitely see on the 2.0 side, like once it launches and there's a lot of users. But right now, I mean, like so far, I don't think that's a dimension in which we're kind of particularly failing.
Okay, and if I may ask, okay.
Going into 2019, other than fintech, what are the top 3 industries that would be embracing this Ethereum 2? And if I can question this, when can we see the Ethereum back at 14 plus?
Where can we see what?
Ether back at 1400 and above.
Okay, no. Okay, so I guess in terms of applications, I think, finance is a big one. Outside of finance, I personally am excited about the very different suites of non-financial applications. So like I talked about, certificate revocations. I talked about things like putting data on the blockchain to verify that it was published or that it was not, or that it's still valid until some point in time. As far as industries go, like gaming seems to be interesting, but in the short term, I think plasma chains could be really good for that. Is like the area where sharding really shines, as opposed to things like plasma chains, is where you have applications that are more complex than just payments or payments in exchange. And then in the longer term, I expect to just see sort of more and more just regular random stuff that right now you would do on the internet. At least kind of cores of it become possible to partially do on blockchains as bigger scalability gets proven out. There's and as I mentioned, like all of these non-financial application areas are interesting, and things around like key revocation, around account management, just maintaining high value non-financial data. On the financial side, in like tokens and creating these kind of efficient open marketplaces where assets created by a lot of different people can easily interface with each other is also really useful. There's a lot of these applications that have to do with trying to create a sort of common data store so that companies in different industries can coordinate with each other without having to go through some central authority, and that's something that you totally can do on blockchains, but you need more scalability for.
Curious if you're considering long-running partitions in the order of months to years in the shard system, and if you're dealing with shards that might accelerate well beyond, so different speeds. Some shards in small regions might be able to go drastically faster because latency is much smaller.
Yeah, great questions, and yeah, quick answer is yes. Having shards that can't talk to each other for a long time turns out to be a really great boon for scalability. If they only sync up infrequently, that creates less overhead. The heterogeneous sharding, where you have like different shards at different capacities, is definitely super interesting technology. However, it also introduces security concerns as people who maybe notice that one kind of shard is underserved can bring a lot of capacity on there and take over to attack those shards. And so there's a certain amount of liquidity that's required in the market for heterogeneous sharding for it to be secure. And so I would say it's not a sharding 1.0 thing. Neither of these are sharding 1.0 things.
I actually have a section in the sharding FAQ where I think I cite you as being excited about this sort of thing. My response was kind of no initially for a couple of reasons. I mean, one is that it's complicated. The other is that if you start having shards where the kind of partitions have structure to them, so we talk about a San Francisco shard and a Toronto shard and a Europe shard or whatever, then the problem is that implies that nodes have a choice of which shards they're part of, which then implies that things like these 1% attacks that we've solved with random sampling start to become a problem again. So I guess one question is like, to what extent do you specifically need base layer shards, or to what extent do you need mite structures that kind of look like sharding in a really abstract sense but aren't sharding TM? So like plasma chains, for example, make sense for that. Another question is, can we design sharded systems that kind of support all of the different ranges of security? And that's definitely something we're interested in. But like, once again, Twitter trolls want us to ship. There has to be a chopping block, and like that ended up on the right side.